So there is another conservation law that we cannot have an analog for classical physics. So this new conservation law is called the conservation of strangeness. So it started in the 1950s where they were experimenting with kaons, lambda, and sigma particles. So as they were discovered, they exhibited a strange property. So for this interaction, this pion minus interacting with the proton, it seemed to produce the kaon plus the lambda naught, but it doesn't seem to produce a kaon plus a neutron. So even though the second interaction conserves energy, conserves momentum, angular momentum, and charge, they don't seem to observe this kind of interaction in experiments. So this is what they noted in the interactions. So these types of interaction, they always seem to come in pairs. So the kaon and the lambda particles always seem to come in pairs. And these particles are produced by the strong force, but they decayed longer than expected. So normally when particles that interact with the strong force are isolated, they would decay very fast. But as these particles were isolated, they seem to decay as if they interacted with the weak forces. So in order to explain this type of interaction, they assigned a new law, which is the conservation of strangeness. So for the strangeness quantum number, they assigned +1 for the kaons and -1 for the lambda particles. So an example is the earlier interaction. So a pion minus interacts with the proton. So they both have an initial strangeness number of 0. And after the final reaction, the strangeness number should still be conserved. And for the kaon, we have 1. For the lambda particle, we have -1. So adding those two would conserve the strangeness number.